Again, very warm welcome. Our next talk will be Beyond BLE, cracking open the black box of radio frequency microcontrollers. It will be given to us by Adam Bathory and Robert Pafford, and it will be including a live demo of a jailbroken RF receiver. If you are watching this talk online and you have a question, you can use our channels on Mastodon and IRC. We have the Signal Angel monitoring, and you can use the hashtag 38C3glitch. Please give a very warm welcome and applause to Adam and Robert.
All right, hello. Thank you everyone for coming to our talk, Beyond BLE, where we hope to look at some of the deepest secrets hidden inside some of these commodity RF receiver microcontrollers. Quick introduction, who are we? My name is Adam Bathory. I'm a hardware security researcher by day, mostly looking at side channels, fault injection, that sort of fun stuff. Also a reverse engineer, sometimes even a forward engineer, certified Silicon Zero O-Day enjoyer, and notably not an RF engineer, or at least I wasn't until this project kind of forced me into being one.
Hey, I'm Robert Pafford. I'm a forward and reverse engineer, but typically a reverse engineer out of necessity. I'm experienced with MCU development, embedded development, and I'm pretty decent at staring at undocumented registers and trying to figure out what they do.
All right, so quick background. As you probably know, the market is flooded nowadays with low-cost RF microcontrollers. Like you probably recognize a bunch of these, the low-cost ESP32 series, the NRF entire family from Nordic, TI CC26 and CC13 line, and a bunch of similar ones. And it's been an interesting point now where the RF hardware in these has enough DSP power to do at least 1 megabit Bluetooth modulation, demodulation, and potentially a lot more when you get into Wi-Fi tier chips. But an interesting commonality is that while you might have a SDK, you have at the very least a reference manual for the user programmable microcontroller side. There's basically zero documentation on the actual inner workings of the RF peripheral. And these manufacturers instead opt to treat it as this opaque black box that they give you maybe some API to talk to, but refuse to actually document the inner workings of. And we saw this and we thought, hey, that's not cool, and we want to change this. And as we like to say, I paid for the whole chip, so I want to be able to program the whole chip. So the specific genre of RF microcontrollers that we're looking at is TI SimpleLink line. This is a pretty large family of both 2.4 gigahertz and sub-1 gigahertz RF transceivers and transceiver plus microcontroller combo. And the ones that we'll be looking at are these combo units. They call them the 13 line for the sub-gigahertz and the 26 line for the 2.4 gigahertz ones. And among there's a couple special part numbers that can do actually both sub-gigahertz and 2.4 gigahertz in the same chip, albeit with obviously different antenna. And within this, there's 3 main generations. You have the X0, the first one originally introduced around 2015, codenamed Chameleon. These have the RF radio tied to a Cortex M3 at 48 megahertz, which is what the user programmable microcontroller is. Then a couple years later in 2018, they released the X2 Agama line, which basically just bumps the CPU to a little bit more powerful M4F, among a couple minor tweaks and improvements throughout the chip, a little bit more SRAM, stuff like that. And then more recently, they have the X4 line, just upgrading to a Cortex M33, notably with Trust Zone now. The specific chip that we chose to target is the 1352R, which is one of these dual band units that we mentioned. And for analysis, we wanted a fully featured chip, meaning both sub-gigahertz and 2.4 in the same chip, but also the most protocols we can get inside one box. So this chip can do Bluetooth LE5, Zigbee, some other 802.15.4 modes, TI proprietary modes, which you might recognize as being compatible with the CC1101, which is what the Flipper Zero uses as their transceiver, and some 2.4 gig proprietary modes. This is interesting for us because we also want to look at how TI differentiates between different variants in these product families and how they lock out these supported protocols on lower end models. And also, looking at a multi-band chip like this increases the chance that we can get something interesting with being able to retune the radio to other frequencies. If you choose a part that has only 2.4 gigahertz, not necessarily from TI, like a super cheap Bluetooth-only chip, there's a chance that the RF hardware physically can only do 2.4 gigahertz, and maybe even physically can only do the Bluetooth modulation in hardware. So that would be interesting to look at, but not as interesting from a reprogramming SDR approach, where this chip that can tune to many different bands, there's a chance that the actual radio hardware has a lot more capabilities than maybe they're letting on.
So with the an interesting thing about the SimpleLink that really drew us towards it is the proprietary radio format. Because most other microcontrollers, it's prefixed to Bluetooth or some like Zigbee or LoRa, and the protocol is already pretty much set up to higher level like protocol standards. But proprietary is a very basic modulation scheme where you get to send raw RF symbols out on the antenna. So it supports various modulation schemes that you can configure, such as 2GFSK, OOK, and DSSS, which you can configure with their tools. And everything is abstracted away into a simple transmit and receive of a packet, but they don't have anything higher level than simple transmit and receive. So this is a lot better lower level access than you'll get with most microcontrollers, and is a great starting point for actually trying to figure out how to gain full control of the radio PHY. Part of their SimpleLink line is called TI Smart RF Studio, which allows you to actually get the radio transmitting and receiving without even having to touch any C code. So it directly talks to the radio and generates all the C headers you need to configure the radio. And they actually don't even give you some equations, and instead, I would say, refer to this tool to figure out how to configure your radio. And the flexibility of these proprietary modes makes it very interesting compared to your standard Bluetooth microcontroller. But all this reconfigurability means that you need to have a very versatile RF subsystem. They're not just going to block it off in hardware and say this block only does Bluetooth. They need to have you be able to reconfigure the radio in ways that you can support all of these modulation schemes. So there's no documentation for this hardware, though. So they really just say use TI's provided API to actually figure out how to use it, and they leave it at that. So our next approach was actually figuring out how do you use how does TI's provided API actually control the RF hardware? Because at the end of the day, when you make microcontroller firmware, it has to compile down into a flat binary image. And so you can actually look at what their API is doing under the hood and what registers it's actually talking to obtain to control the RF hardware. But unlike all the other peripherals in this chip, the RF actually uses a higher level API of messages that's being sent into the peripherals. They don't actually ever touch the RF hardware. Instead, it talks to this thing called the, quote, command packet engine in their datasheet. And it's a basic mailbox system sending predefined commands to start the RF, tune to various frequencies, and transmit and receive. You never actually see how it's configuring this very versatile RF chain to actually achieve a specific goal. So what is this command packet engine that you're actually talking to? It's actually a bonus CPU core inside of the chip. It can't actually be programmed by the user, they say. It's fully locked away. And it's the gateway, or some would call firewall, to the rest of the RF subsystem. It's designed as a dedicated processor to do real-time management, so while you're doing other parts of your application, it can respond to high-priority signals from the RF subsystem and make sure that it's meeting the timing requirements. So it's an ARM Cortex M0 microcontroller that's put in there, and the really interesting part is that it runs from its own private ROM. You can't actually access this ROM from the main system bus, so you have no clue what it's actually doing. It has access to the rest of the system bus, though, so it can read configuration from your main system RAM and read flash. But it also gets extra privileges on the hardware bus to talk to RF-specific peripherals that you can't actually talk to from your main SoC. So we need to get code execution on the CPE to dump the ROM and be able to talk to the rest of the RF before we can continue and do anything else.
Yep, so like Robert said, we need to get code execution or some way to dump the CPE ROM. And the CPE ROM is not mapped in the Cortex M4's address space, but lucky for us, its SRAM is mapped in our system address space, and it's even nicely referenced in the TRM. And looking at it, it's 4K, and it looks like mostly random and garbage data. So without having any obvious patterns in the RAM and without having really any other documentation to go off of, we have to do some blind exploitation. And it's around this time we noticed that the SimpleLink SDK contains what they call patches, which they get copied into this RFC RAM or CP RAM. TI even calls it a few different things depending on which document you look at. And because it's doing this to add new features, we presume that, hey, there's probably a mechanism somewhere with this patch system to load executable code. So looking at, for example, like one of these patches, it's an opaque binary blob that TI gives you, and some things they've used it for is to add like Bluetooth coexistence features, add DSSS modulation, add some more like modes to the proprietary radio protocol like modulator scheme. And the C code running on the Cortex-M4, the user microcontroller, loads this into CP private SRAM, that address space we just saw, and doesn't really do anything with it. It doesn't do any processing. It just basically mem copies it in there. But whatever this is, it's powerful enough to allow TI to release entirely new protocols for existing chips without having to change the ROM. And we're like, hey, we want to do this too because we can't change the ROM, but we also want to be able to add new protocols for existing chips. So trying to disassemble chunks of this blob yielded valid thumb code, and that's more credence to the fact that this is executable code. And interestingly, there's seemingly no encryption or signatures on it whatsoever. So we decided to do something super simple, basically just knock out anything we could see as code and add a couple jumps to a little bit of shellcode we put into the main M4 SRAM. And this shellcode is basically a small memcopy loop, try to read from the bottom of the CP's address space where the ROM is presumably at and see, hey, can we get any data out? Like, surely it can't be this easy. Well, we load the patch, and turns out it is that easy. So this got us our first look at the not-so-secret ROM now of the CP and the hard-coded RTOS-like system that it runs to do the RF management. Now, it would be nice to have a way to get codec-sec reliably and easily on this CP core without having to always do some weirdness with patching and putting codec-sec shellcode in RAM. So as we started reversing this ROM and the API mailbox commands that it processes, and of course we found some undocumented ones in the ROM. One of them, OX0811, just so happens to be a nice function that TI gave us or left in there from their debugging that, for all intents and purposes, literally just calls a function pointer that you give it over the mailbox. So that's super nice. That's baked into the ROM on every chip, and it just works. So now that we have the ROM dumped, we can do some more reverse engineering and figure out how these patches are actually intended to be used. It turns out a majority of these ROM functions, actually like almost all of them, have a little check at their function entry point that looks at an offset in a hard-coded region of the CP SRAM, like where those patches are copied, that says if this patch is enabled, actually detour the execution of this function into a new function pointer given in the CP SRAM. So this lets you basically override almost every function in the ROM, including some interesting ones like IRQ handlers, NMI handlers, hard fault, which you might think shouldn't be able to be bypassed, but no, you can. And as a result, these patches are basically powerful enough to be able to entirely replace the CP ROM. And we want to do this. We want to make our own patches, right? We want to run our own code and basically run our own firmware in there. And to do that, we've made a little tool chain of sorts that lets us compile C code into the patch format that is easily loadable by the rest of TI's SimpleLink Studio SDK. And we can reuse this mailbox hardware to pass messages back and forth to the main Cortex-M4 and basically have this C2 command and control stub running on the CP, which we can then use for further reverse engineering deeper and deeper into the RF core.
So I'd like to first call out this screenshot that we found on the TI forums of we're not the first people to find these patches and wonder, hey, can we write custom protocols for this chip? And they actually asked on the forum, hey, are we able to do this? Can you provide any documentation on it? And a TI engineer said, quote, to write a patch requires knowledge of the chip outside what we are going to include in the documentation. So we're now going to go into part 2 of the presentation.
We're going to do exactly that.
Yeah, gain knowledge of the chip. So one of the next steps when we were doing reverse engineering is we found that CPEs weren't the only thing that could actually be patched in the chip. It actually contains 2 other types of patches known as the RFE and MCE patches. These don't disassemble the ARM code. They were very different from the CPE patches and get loaded into separate RAM addresses. There's very little info on actually how, what these are, how they work. They don't even say what they stand for inside of the technical reference manual. And it seems like it was kind of like in there by accident. This is a screenshot from the technical reference manual explaining an override, which they don't ever explain how to use, which calls out what that there's an MCE and RFE. But there's some very interesting points in here of that it appears to be some sort of processor which can be loaded either from its own ROM or RAM, but it's definitely not ARM from what we've seen in the patches, and there isn't really much additional information that we could find anywhere in their official documentation on it. But we got really lucky when we were looking through some, not really documentation, but instead the source code of the SDK. And one version of the SDK didn't actually get the patch exported properly and included some extra info inside of it, including a full assembly listing for the MCE patch with all of the headers. So this reveals a completely new instruction set, assembly opcode matching, and you can actually go through and start to figure out what this MCE actually is. We did fuzzing for the rest of the instruction set to get a full opcode map, and so now we have the I/O space mapping for the MCE thanks to the headers. We have a full instruction set, and we have a lot of very interesting comments that can teach us what this MCE is actually doing. So what is this MCE and RFE? According to the document, it refers to it as the top SM architecture, and it's a very simple RISC CPU instruction set. It's a 16-bit word addressable with 16 registers and a very small hardware stack, so you're able to have subroutines. But there's no ability to really write to memory from what we found. It has only read-only data, has a read-only data and instruction bus, which can point to one of 8 ROM banks which can be selected, or a RAM bank which can be used to load in patches. There's also an I/O bus which allows it to communicate with the RF hardware connected to that chip, which is what allows it to kind of interact with the RF analog blocks and actually do acceleration and perform real-time hardware acceleration of the chip. So we want to analyze these ROMs that they can clearly be booted from, but you can't actually read the other address space when you're booted from RAM to load custom code. So we couldn't figure out how to do it with the instruction set, but luckily TI made a tool for that built into the hardware. There's a hardware peripheral which is designed to just dump ROM into RAM, and there's even a documented CPE command that just does it for you. And so this is a ROM right here. We were able to dump it out, and we even created a full Ghidra plugin to look at the ROM and actually start to understand what's going on. And thanks to the headers, we were able to extract from the MCE patch. We were able to get the addresses as well, and really start to piece together what the RF hardware looks like under the hood. So now that we have all these bits of binaries and ROMs that we've dumped, we can actually start to piece together what the RFE and MCE actually do. So first, we were able to figure out what they stood for. RFE stands for RF engine, and MCE stands for modem command engine. So the RFE is primarily responsible for real-time control of the RF front end. So this is things like when you want to see how strong the signal is coming in on your Bluetooth, it'll estimate that and report it to the main CPU. It'll also do automatic gain control of the incoming signal and any real-time configuration that needs to happen right when you start transmitting. The MCE is another core which is responsible for the real-time control of the modem block. So this, again, does that startup configuration, but it does on-the-fly reconfiguration of the various accelerator blocks and sequencing the various stages of packet transmission and reception. And this is what's really interesting to us, because if you want to implement custom protocols, you want to use the modem and use all the hardware you have available to actually decode and process data in ways that they didn't originally design it for. So just a quick review on where we are right now. We have full code execution on the CPE with a ROM map. We have instruction maps for the custom CPUs of the MCE and RFE, as well as the ROMs to understand how they use the RF hardware, and a full register map for part of the RF chain, and more specifically, a very interesting part of the RF chain which is used for processing custom protocols. And we have really good guesses for how the rest of the subsystem works based off of the reverse engineering on the ROMs and analyzing some patents. So now we're going to introduce the RF subsystem.
Yep. So the final part of this, after you have the Cortex-M4, the user programmable MCU, you have the CP Cortex-M0, you have the MC and RFE little like embedded controllers. The final part to this puzzle is the RF subsystem, the actual analog part that does the signal transmission and receiving. And on screen is what TI basically give. This is basically all they give you in the manual. It's, you know, you have a couple triangles, a circle, like 2 blocks in there, like sure. So what actually is this? Well, the quote-unquote analog section isn't even really that analog anymore. TI calls it their ADPLR, like their all-digital architecture, and it's basically TI trying to move as much of what was previously analog RF signal chains into the digital domain. So things like your digital LO, like your oscillator, you have like digital mixers and your IQ ADCs, and the digital modulator for the transmitter section. And this is really to reduce cost, complexity, power, and things like, even things like variability between like different dies. So you don't have to do as much tuning in the factory. And it's all different like pieces to making these chips like easier to mass produce and lower cost, lower power. What this means though is that most of this processing, instead of occurring in the analog domain, is done in these little DSP accelerator blocks, which is what the MC and RFE, as you call, are in charge of like manipulating and setting up. And as we'll see, this analog section is very complex, and you could talk about this for hours and hours. But we've luckily stared at patents for hours and hours to piece together a lot of this. And TI did in fact patent a lot of their this architecture. There's a couple on screen, but if you go down this rabbit hole, you'll find an entire like series, I think like over 100 patents, I believe, that encompass different parts of this like receiver. So, for example, of like what one of these patents looks like, this covers the like a little bit of a higher level view of this analog section. What they have labeled as script processor in block 60 on here is what we believe to be like an MCE or an RFE state machine mini RISC thing. And everything else is these like accelerators that they have to implement their digital architecture. So in this case, they have their digital PLL, the thing that generates the frequency that you're receiving and transmitting on. Things that, yeah. One more. Zooming in a little bit to that PLL. This is just, again, more TI patents on how they're implementing this. And really where this is useful for us is that we can use this as a reference to correlate to some of the I/O and addressing and I/O and algorithms that we're seeing in these ROMs. So for example, like when the RFE is setting up, doing some certain equations in math that we think is PLL math, we can actually cross-reference like individual wires in this chip, like individual registers. Like we might see something like the frequency FREF, frequency reference being calculated with like a well-known PLL equation and being written into a register. Well, we can actually see that like if you look in the bottom left corner of this diagram, thanks to the pattern, we know that, hey, this is actually a wire physically existing in the chip that goes into this block, into that block, and we can basically make more educated guesses on how the analog part works. We can't go super in depth, unfortunately, right now for a lack of time, but we put together this new diagram, right? So instead of TI's like circle in 3 blocks, this is how we see the inside of the RF modem and analog chain. So what you'll notice, we have the I/O bus talking to a lot of these sub-blocks, and these are the actual DSP accelerators that we were mentioning. So for example, you'll see like phase correlators, a Viterbi decoder, you'll have an FEC encoder, right? Stuff that terms that you'll be very familiar with if you look at any of the low-level modulations for things like BLE PHYs or like GFSK, DSSS. And this is the view that we get from REing the view of the analog bus as seen from the MC. There's one other interesting thing that we want to get back to, which is the CP-ROM. Well, we mentioned that some versions of the chip have certain protocols enabled, some versions of the chips have different protocols enabled. And how does TI do that? Well, it's very likely that each variant that they claim is actually just the same die with certain features fused off. This is very common in the industry, and it basically saves you the time, the cost, the complexity of having to design and manufacture different chips for what is almost the same application. And this hypothesis was reinforced when we were seeing these jumps in the CP-ROM that seemingly didn't make any sense. Like they were jumping into pages of like all FFs, but if you dump a ROM from a different chip, like in the same family, just with different protocols enabled, there would be code there, but there might not be code in a different page. So we believe that every chip that they make, every die has the entire CP-ROM that exists, just with different pages of it disabled if you're not allowed to use that protocol. And that protocol, these bits, this bit mask, comes from an OTP register TI sets in the factory that basically determines which chip in the family you become and what you're allowed to what you're allowed to encode, decode. And the CP-ROM checks this OTP value before it starts to enable any protocol. But as we mentioned before, hey, patches can basically override everything, right? And sure enough, patches could override this check. And we believe TI knew this, and as a secondary protection measure, there's a little hardware block in there somewhere that also reads this, this OTP lockout register, and actually in hardware disables readback of those ROM pages. So if your protocol isn't enabled on that OTP bitmask, even if you were to patch out the check in the CPE-ROM, the hardware bus does not let you read that page in ROM, even though it exists. You just get FFs. However, like theoretically, if you were able to change that OTP value, you could turn those ROM pages on and off. It's in the chip.
So part 4, we actually get to write the custom RF firmware. So, AKA, I paid for the whole microcontroller. I'm going to use the whole microcontroller. So creating these custom, now that we have all of this info on the MCE and all the various subsystems on the chip, we can actually start to understand enough to write custom protocols in the MCE and create assembly patches for it. So for this example, we're going to implement a narrowband FM demodulator with the SimpleLink. So narrowband FM is an analog modulation scheme, which the SimpleLink does not do. They only support digital modulation according to the datasheet, but we're going to leverage the IQ receiver architecture and actually tap off before it does any sort of digitization and actually be able to demodulate this analog RF signal. So this is a quick diagram of the patch that we're going to implement. We're going to use the same, again, IQ receiver, but we're going to configure the blocks to just do a phase differentiator to effectively compute the instantaneous frequency at that point in time. Do a little bit of cutoff so you don't get static when there's nothing transmitting, and then low pass it for only audio frequencies and send it right out to a speaker. So this we can do with a series of MCE and CPE patches, and we actually have that running on this right here, which we'll show in a little bit. In order to actually do this, we had to develop a full tool chain to do it. You theoretically could write the MCE patches by hand, but when you're making something this complex, it's a lot easier to work in native assembly, which we just so happen to also have, thanks to that one IQ dump file. And so we wrote a assembler tool chain for developing these MCE patches, and it's going to be available on GitHub right after this talk. So, and we actually, one fun thing we noticed was we caught a syntax error in TI's patch, which is quite interesting. So I'm pretty sure that our tools are better than TI's internal tools. So. And just a few small notes on future work. There's a lot more to explore on this device, messing with all the analog front end and frequency tuning to achieve new frequencies that you typically can't get. There's also a lot of RE that can be done with the DSP modem blocks. We're just using a few here, but if you can enable a lot more of these blocks, you can implement a lot more higher level and advanced protocols, stuff that TI typically wouldn't have implemented themselves. And this can actually be a path to an ultra low cost SDR because it has raw IQ samples that you can tap off, which Bluetooth can run at 1 megabit minimum. So you can definitely get those high frequency IQ samples out and begin to do more advanced processing on the chip for stuff that you typically won't be able to do with just the MCE. And also investigate other chips in this SimpleLink family, such as a Wi-Fi transceiver, which will have much higher data rates and thus much more powerful DSPs. So there's a variety of different ways we can branch off and look and investigate more here. So now we get to the interesting part. We have a live demo, so hopefully this works. we're going to have Adam here mute his microphone and connect it up, and we're going to do a transmit from a radio here, and we're going to pick it up and do a narrowband receive from the SimpleLink. So I'm going to power this up.
Stand away.
Check. Hello, 38C3.
So thank you for coming to our talk.
Also, thank you to you for giving the talk. We already have a question from the internet. If you don't want to attend in a Q&A session, please leave the room in a quiet way. Signal Angel, will you read the question from the internet?
Yes, there is a question. Do you have any experience regarding the lower than publicly documented access to STM32 Bluetooth-enabled chips?
Sorry, could you repeat that?
Do you have any experience with the STM32 Bluetooth-enabled chips?
Not a lot. I've personally used them before as intended, but that's not one that we've looked at for RE yet, unfortunately. From the little that I have looked at, we believe they might be using some similar similar concepts for how they do a lot of this receiver. But if being different company designing their own IP, there'll be probably a lot of differences in the the low level part of that.
We have another question at microphone 3.
So, hi, I also stumbled on the TopSM assembly file and then did nothing with it, but I noticed that the SimpleLink microcontrollers also have what's called a sensor controller core, and those look very similar to the TopSM thing, except the I/O bus is different. Have you actually looked into that?
Yes. So we actually we use the sensor controller. We kind of data mined everything we could find about that to see when we were originally looking at the instruction set to see if maybe we could get lucky and it was the same core. You're right. It is very similar. We think they're probably either a version, either they were from a common ancestor, or they just stripped out features. But we noticed that there's enough differences in how the instructions are encoded that it wasn't at the end of the day really useful to figuring out the things that we really needed to, like the bus read write instructions. Those were basically completely different.
Okay, thanks.
Von Wan, the mic is yours.
Given the complexity of the radio side, TI has to have a way to debug that for themselves. Have you looked into re-enabling the JTAG chain on those chips for that half of a chip?
So
on the M0 core?
Yeah, we've actually looked at that for the Cortex M0, and unfortunately, it seems like they disabled JTAG on that chip. We aren't entirely sure how they did it in development. We're assuming they had an FPGA that they were developing it on. But if you look in the Cortex M0 address space, the debug hardware doesn't even get mapped in, so there's no way to JTAG in.
The M0 straight up does not have debuggable capability. What they do for debug, that our theory is that one, the firmware has references to FPGA, obviously, so they use FPGA for development, and also there's a couple blocks in there in that. In the overall system architecture, they have a couple of blocks. It kind of has almost like a basic UART between the modem cores and the RF side and the outside world that you can put on an undocumented GPIO MUX. And if you do that, you can have a basic UART link to this core, and they use that to they literally just have printf debugs. They basically have printf debugs in the ROM, and that's all you get.
Next question from microphone 2.
Fantastically complete effort. Do you have concrete plans to produce a general purpose SDR with this? And what kind of bandwidth and sample rate do you think could be achieved by such a board?
We don't really have any concrete plans right now. We have a few ideas on things we could do.
We need more free time.
But yes,
we'd like to.
Yeah. But that's also why we're pushing a bunch of these tools out on GitHub, because we want everyone to mess around with these chips and figure out what you can do with them, because the more people looking at them, the more you can figure out. So.
And what sample rate did you achieve with your IQ setup?
Right now, when we were just doing the narrowband FM, we're running 50 kilohertz bandwidth with IQ, but this is just for audio. But I'm sure there's other configurations with Bluetooth you can push it faster. So
Yeah, don't quote me on this, but I believe you can get 2 meg samples, 1 or 2 meg samples out of the IQ, like the ADCs.
Thank you.
Microphone 4.
Out of morbid curiosity, do these custom ISA software blocks look like handcrafted assembler to you, or did they write a compiler for it?
For the MC RFE?
Yes.
Yeah, I'm almost certain it's handcrafted. They have every line of assembly commented.
So they basically tortured someone for custom RF code, okay.
Microphone 3.
Yeah, so in terms of using this as an SDR, on the TX side, as far as I can see from the diagrams, there's no IQ modulator or anything. You're limited to constant envelope modulations and so on.
Yes, so that's unfortunately one of the drawbacks for these, primarily BLE chips. They don't have they have IQ receive, they do not have IQ transmit. And that's also why we listed the CC32 series as a future work, since being a Wi-Fi chip that would have IQ transmit. What you can get is obviously analog modulation and some level of phase modulation, but that depends on how well you can control the ADPLL, since you need to basically direct drive the phasing in it. But there's no IQ, unfortunately.
Yeah, thank you.
Microphone 2. You had a question?
Yes, thank you for the talk. I may have missed that part, but when I remember looking into developing for the CC chips, there was some workbench that needed to be bought. I think the entry level was quite difficult. Is it still the case?
The Code Composer Studio, which is what we use to develop it, you can get the SimpleLink SDK and the Code Composer Studio for free. Some of the earlier versions was Windows only, and I think it might have been the case, but nowadays it's all open and cross-platform.
Sounds good. Thanks.
Microphone number 3.
Hello, guys. Excellent work. Congratulations. My question is about, have you checked what is the frequency agility of this chip? How wide is the tuning range that practically works?
It's quite interesting where there's windows where it works that they let you transmit, and there's other windows that don't. We're still trying to figure out if those are hard limits in hardware or more of band restrictions. But it's various windows, but you can go all the way down to 140 megahertz, and there's up to 1 gigahertz, and then 2.2 gigahertz to 2.7 gigahertz. But
it covers a lot of the range as low as in the hundreds of megahertz to, I think Robert got hit 2.6, 2.7. The interesting thing is that part of those ranges, these gaps aren't a software lockout. We've seen the PL just fail to lock. We think there might just be missing VCO bands, since there's no reason that TI would need to design and validate a 1.5 gig VCO band in this chip. But that's requires some more further research to do your own PLL driver.
The next question is from microphone 4.
Hi, so does the CC chip actually do any form of self-calibration? So on the ESP32 we found that it actually calibrates itself by shorting the TX and RX IQ paths, and does it do that as well?
Yeah, there appears to be some calibration and feedback during the startup, where it will, but a lot of this calibrations are loaded in with trims that they did during the factory. And there's only a few small parts that they do. But we have found debug references to being able to loop back that info, which we're assuming they do during those factory tests when they load all of those trims in.
They build in a pretty good amount of observability into the TX chain. And they don't use a lot in production. We believe they for stuff like BLE or simpler protocols, you can just one and done it from the factory. But there is a good amount of observability and different reference paths you could actually mux in yourself if you did want to do a self-calibration algorithm.
I do believe we have time for one last question, and our signal angel have one from the internet.
Do you think there is a chance that, or a risk that Texas Instruments would apply a patch that would block your access?
We don't think that there's any way to block the access without implementing some sort of signing, because TI themselves heavily relies on these packages for when a new Bluetooth protocol comes out or a new edition. They make these patches themselves, so they're not going to disable patches from what we can see.
And also, in every chip that currently exists, there's no way you can disable this, because there's at least 3-4 ways that are built into the ROM that you can just get permanent code execution, if you can even call them that, right? They have it baked into the ROM to just call a pointer. So there's nothing they can do about chips that exist.
Again, thank you so much. Can we have a big applause?